one basis vector and one matrix. I'm going to take this equation right here, and I'm going to move it over to this side, to where I have A, V, minus lambda, V equals 0. I'm going to factor out that vector, so now I'm going to have one matrix, A minus lambda I, where I is the identity matrix, of V on the outside equals 0. So this is still the eigenvalue problem, however, it's in a form where I have a single matrix times a vector is equal to 0. Now, the zero product property, something we learned from algebra, means that if one of these is non-zero, that means the other has to be the one equal to 0. And in this case, what we're looking for is called non-trivial solutions. Because 0, 0 times anything is obviously going to be equal to 0. That's called the trivial solution. And we're looking for non-trivial solutions where this V right here is going to be non-zero. We're going to go ahead and declare that this V is always going to be non-zero. Therefore, in this equation, all we're looking for is this matrix right here. And so, we can't really have a matrix with like non-zero terms or elements inside of it equal to 0, so we're going to take the determinant instead. And so now this is still the eigenvalue problem.
Can you explain what the determinant is?
The determinant is sort of like a single value that represents the matrix as well.
Okay.
It's hard to describe, but it has some purposes. Like, for example, a cross product between two vectors is going to be the determinant of that matrix in a certain basis. And if you took your numerical class, like, they discuss determinants a lot more. But I can show us how to take a determinant.
Yeah, okay.
By the way, for this exam, you will not be asked to take the inverse of any matrix, and you will not be asked to take the determinant by hand of anything beyond a 2x2 matrix. So you should know how to take the determinant of a 2x2 matrix. And let me show you that right now. So I'm going to have a matrix A, B, C, D, like this. And my goal is to take the determinant of it. What I'm going to do is I'm going to start with these diagonal elements, and I'm going to multiply them together. So I'm going to have AD, and then I'm going to subtract the off-diagonal elements, minus BC. And these are all just numbers, so this should also be a scalar value. This is your formula for the determinant. We good with that? Okay. So the next thing that we're going to do is we're just going to ahead and use this. Go back up to our example. Erase these. So another property we want to be aware of is the inverse of a diagonal matrix is equal to the inverse of all of its elements. So I'm going to say D is a diagonal matrix. Which means that it's only going to have elements on the diagonal. Just like this one right here. And so the inverse of a diagonal matrix is going to be just the inverse of all of its elements. I don't really know how to formally write that, and so let's just do that with this one. So M1, 0, 0, M2. The inverse of a matrix like that is going to equal to 1 over M1, 0, 0, 1 over M2. That's the inverse of our mass matrix right here.
But we won't have any inverses, you said?
No. Like, that was helpful in the homework to know,
Yeah.
but you probably won't have to do that on the exam.
Yeah.
In fact, you won't have to do that on the exam. So, now, with that in mind, I'm going to do one more thing. So, we're going to assume our solution is of the form x, it's a little x equals big X times cosine of omega t. And when we differentiate this once, we're going to get minus omega x sine omega t. Differentiate this twice, we're going to get negative omega squared x cosine of omega t. So if we plug these in to our equation right here, we're going to, or if we plug these in to this equation right here, we're going to get an output of negative omega squared m x plus k x equals 0, like so. And what we can do is now multiply this entire equation by the inverse of m that we found before. So when we do that, we're going to have negative omega squared x plus m inverse k. I apologize for my inconsistency with notation. K x equals 0. I can factor out this x right here, and then now we have the eigenvalue problem. M inverse k minus omega squared I all times x equals 0. Notice the similarity in forms to the eigenvalue problem that I wrote before. So now I'm going to go ahead and declare that the omega squared will always and forever be the eigenvalues of this system. So I'm going to formally define lambda as omega squared. That is important. You want to remember this. And so now I'm going to rewrite this matrix up here in that form, which is going to be 1 over m1, 0, 0, 1 over m2 times our k plus 1, k1 plus k2 minus k2 minus k2, k2 plus k3 minus our lambda times identity matrix, all times x equals 0. All right. Now, we've reduced it down to the form of the eigenvalue equation. We're going to do a little bit, so we have one matrix expression times our vector is equal to 0. Now what we need to do is we need to take this and we're going to put it into one matrix. And so now we need to do some matrix multiplication right here. So let's do some matrix multiplication. I'm going to have A, B, C, D times D, E, F, and G. When we are multiplying matrices, there's a very specific order, and matrix multiplication is non-commutative, which means that this matrix times this matrix is not equal to this matrix times this matrix. So when you have them set up like this, it's very important that you remember the order. So what we're going to do is we're going to have another 2 by 2 matrix in this case, where it's like the number of columns in this matrix must be equal to the number of rows in this matrix. And when those are equal, you're going to have a square matrix. Yeah, right, yes, 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 okay. So, here's how we're gonna do this. I'm looking for the top left element in this case. And so I'm gonna take the top row, left column, multiply those together, and then sum them. So top times left, which is going to be AD plus BF. Make sense? I literally like to think of it as taking these and just boop, putting them right there and then summing them. So that's what we have right here, AD plus BF. Now let's do the top right. Top right, so we've got top row, right column. We're gonna distribute and sum, so now we're gonna have AE plus BG. All right, now let's do the bottom left element. Bottom row, left column, CD plus, whoops. Guess I should probably rewrite these, shouldn't I? So it's more clear. So A, B, C, D, E, F, G, H. I know my alphabet, I swear. So we're gonna have AE plus BG. Then we're gonna have AF plus BH. Apologies for that. So we're doing bottom left. So now we're gonna have CE plus DG, like that. And then finally, we're going to do bottom right, which is gonna be, yeah, bottom right, which is gonna be CF plus DH. And there we are. Making sense so far? Awesome. So now with this in mind, we're going to go ahead and do that with our M inverse K. All right. So, with our M inverse K, let's go ahead and do that matrix multiplication. So, top left, top row, left column. What's nice when we have these zeros here is you can just forget about that other term. So we're gonna have K1 plus K2 over M1. That's our first term because this is 0, we don't need to add anything. Our second term is gonna be top row, right column. So we can ignore this one because that's a 0. We're just gonna have minus K2 over M1. Our third one, which is going to be bottom left, 0 times this plus that is going to be negative K2 over M2. And then finally, bottom right, which is going to be bottom row, right column, which is going to be K2 plus K3 over M2. That is our inverse M K matrix right there. So this is all fun and good, but now we need to factor in this identity times the eigenvalue. And what's nice is we can just do a little of this right here. Whoop, whoop, and there we go. See how I just took that and subtracted it from each of the diagonal elements? Awesome. Now this matrix is the one we're going to solve for. And this is the matrix we're going to take the determinant of. So we're going to assume that this is non-zero. Therefore, the determinant of this matrix must be 0. So when we work that out, we're going to get a crazy, how about this? Let's go ahead and make this simpler on all of us by declaring that K1 equals K2 and that M1 equals M2 equals, so it's going to equals K equals M. And then we're going to factor out an M over K from all these. So I'm going to say this is going to be equal to 2K over M. This is going to be equal to negative K over M. This will be equal to negative K over M. This will be equal to 2K over M. When we do that, it's just going to be K over M times 2 minus 1 minus 1, 2. Okay. So now we're going to take the determinant of this matrix, so it's a little bit easier. So actually this is going to be 2 minus lambda, and then 2 minus lambda. So when we take the determinant, remember that's going to be the diagonal elements, the product of the diagonal elements subtracted by the product of the off-diagonal elements. So the determinant of this matrix is going to be 2 minus lambda